Okay, so let's get started. So last time we were talking about functions of real numbers, so functions from R to R, or possibly where the domain or codomain is a subset of the real numbers. And we were just running through some of the important examples of functions from the real numbers to the real numbers that we'll be looking at in this class. And we left off with polynomials. This was like our third type of function. So for example, this is just going to be some set of coefficients. So I'll write down like how I would write this and I'll explain. So in general, what does a polynomial look like? Okay, so this is like sort of a general expression for how to write down a polynomial. And I want to take a second to talk about a little bit of the notation appearing in this expression. So first, these A's with numbers below them, these are the coefficients of your polynomial. And these are all just elements of the reals. So these are real numbers. And the subscripts appearing here, right? So a sub n, a sub n minus 1, and then we go all the way down to a1 and a0. The subscripts are just a convenient way to indicate which coefficient you're talking about. So I could have called these coefficients like A, B, C, D, E, and so on. But it's sort of easier to just number them because often our terms will naturally have like some number associated to them. And in this case, that number is just the exponent on the variable x. Okay, so like an example of this might be like 5x to the fourth. So in this case, 5 would be a sub 4 plus 3x cubed. Oh, and then the other thing I wanted to point out is this dot, dot, dot. So whenever you see dot, 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 it's sort of meaning to just fill in following the pattern. So in this case, we would just continue with all numbers from n minus 1 down to 1 and just fill in the terms following the pattern here. Okay, so if n is 10, right, it would be inconvenient to write down all of those terms. There's just a lot of things to write, but the dot, dot, dot just tells me that I should continue on in the same way that I'm doing. So in this example, so maybe we then have 1/2 x squared plus square root of 17 x, maybe we'll do a -1 minus 1. And of course, x to the 0 is just 1. So that's what this last term is in this example. Okay, so why do we care about polynomials? So polynomials are sort of the simplest nonlinear functions. And the reason why that is if you think about, if I give you an input x, how do you compute this thing? Well, you're just doing multiplications and additions or subtractions. So that's like a very simple thing. And that's something that computers can do. So computers get on really well with polynomials. And what you'll see if you go on to take the next class in the sequence, 1301, is that you can use polynomials to approximate any function as well as you would like. So in 1301, you'll learn how, if you say you have like cotangent of x, you'll learn how to write down a polynomial that approximates cotangent of x arbitrarily well. And that's actually how your computer calculates. Like, what is the cotangent of, if you input a specific number, it knows a polynomial that approximates it and just spits out that estimate. So in some sense, like if you can understand polynomials, then you have a pretty good handle on what's going on in other cases as well. Okay, so that's polynomials. Are there questions about polynomials? So another function that we'll see a lot in this course is rational functions. So this is going to be a quotient of two polynomials. You're going to take one polynomial and divide it by another polynomial. So this will look something like f of x divided by g of x, where f and g are polynomials. And here you have to be careful to make sure that g of x is never 0, right? Because we can't divide by 0. And so typically what you need to do there is figure out when is g of x 0 and just remove those numbers from your domain in order for it to be a function, right? Because if it's supposed to be a function, then I should be able to input any number and get an output. But I can't do that if g of x is 0 for some value of x. So let's look at some examples. So say we have 1 over x. Okay, first of all, why is 1? So this is supposed to be f of x over g of x for some choice of f and g. Why is 1 a polynomial? Yeah. Yeah, so we're thinking of this just as being equal to 1. Is that color too light? Yeah, it's kind of light. So you're thinking of this as being equal to 1 times x to the 0. So technically any constant does fall under the umbrella of polynomials. Okay, so this is a function, but we cannot plug in x equals 0. So x cannot equal 0. And so this is only a function. So let's say f of x. Okay, so let's say f of x is equal to 1 over x. Then f is a function not from all real numbers, but we have to take away 0. So it's a function from R minus the set containing 0 to the real numbers. Does that make sense? Okay, so those are rational functions, and you might wonder, like, what does the graph of a rational function look like? And this is something that calculus will help us figure out. So using calculus, you'll be able to tell a lot of geometric information about what the graph looks like by studying the equation for your function. Okay, and then the last type of function that I wanted to talk about was piecewise functions. So this is like a way of stitching multiple functions together. So let me just do an example. This is going to be a way of stitching multiple functions together. And here's sort of how the notation works. So you might define your function to be f of x is, and what's going to happen is we're going to say our function takes on some value for some real numbers and some other value for different real numbers. And so the way that you say, like, here are your options is you put like a big curly brace like that. So I'm going to say my function is equal to 1 whenever x is less than or equal to minus pi. And I'm going to say my function is equal to the sine of x whenever x is, let me scoot this over a little bit. Whenever x is between minus pi and 0. And then I'm going to say it's x over 2 otherwise. So when x is greater than 0. Okay, so, right, so this is a function from R to R. And what it does is if I input some number, like say I put in minus 10, then I have to decide which case minus 10 falls into. So minus 10 is less than minus pi, so I'd be in this first case. So that means that the function outputs 1. So sort of like how this is functioning is whenever you have a specific input, you have to decide which of these conditions is true, and then the function does the corresponding thing. So let's draw the graph of this. So here's my y-axis, and here's my x-axis. And I'm just gonna mark where these sort of like changing points are. So we know the function does something different when x is less than or equal to minus pi. And we know that it does something different when x is, oh, and I should actually, okay, so there's a problem with my function. Does anyone see the problem? Yeah. Right, so we don't know what the function does at 0. So I'm gonna just add an equal sign there. Right, we want it to be defined for all real numbers. Okay, so the function does something different when x is equal to 0, and then those are the only sort of like places where it changes. So, okay, we know the function is equal to 1 for values of x less than or equal to negative pi. So whenever I take one of these x values, my function is just going to be 1. So I get a little line segment in my graph right here. So I'm going to say this is when y is equal to 1. Okay, then between negative pi and 0, the graph is sine of x. So do we remember what is sine of 0? Yeah, sine of 0 is 0. So we know the graph is going to do something like that there. And then what is sine of minus pi? I think it's also 0, right? Okay, so let's draw the easiest way for me to do this is to just draw a little unit circle and try and think about it. So off to the side, let's just like, here's our unit circle. Okay, and so the sine is the height of the triangle that you get when you draw. So if I put a point on this circle, this is x, and then sine of x will be this height, right? So let's make the circle blank again. So how did we know that sine of 0 was 0? Well, if I make my angle 0, I'm looking at this point, and the height of this triangle is 0, right? So which point on this circle corresponds to minus pi? Yeah. Yeah, so this is when the angle is minus pi, right? So I think maybe the easiest way to figure this out is the whole circle is 2 pi, right? So that means that this angle is pi. And so the negative of that would be this, which is minus pi, which actually gets you back to that same spot. Okay, so this is the triangle that we get when we're looking at an angle of minus pi. And that triangle still has height 0, right? So, and then, okay, so we know what the value of this function is. Well, it's going to be a little open circle there and an open circle here. So we know what it does at the two endpoints, and you can imagine sort of what is it doing in the middle. So as I go from 0 to minus pi, I'm looking at points along this arc, right? So the value of sine is going to start at 0. It's going to have negative triangle heights, right? All the way up to when it's at -1, and then it'll go back to 0. So at minus pi over 2, we'll get to 1 and then go back to 0. So here's, maybe I'm going to draw the graph of the function in red just to distinguish it from these like pink. The pink is just like finding locations in the XY plane. Okay, so here's my graph. So at minus pi over 2, we're 1. And along here, oops, it looks like a line. It should be like a curve. So it's looking like that in this domain. Okay, does that make sense, that part of the graph? Okay, so we drew this part and we drew this part. Then the last part of the function is whenever x is greater than or equal to 0, it looks like the linear function x over 2. So we actually do have, when x is equal to 0, we get 0, so that's like a filled in point. And then we have a line of slope 1/2 coming out of there. Okay, so that is the graph of our example piecewise function. Are there questions about this? Okay, so I wanted to say one more thing. So we have a few ways of combining functions. So the first one is with arithmetic. So let's let f and g both be functions from the real numbers to the real numbers. Then if we take any operation, so like addition, multiplication, subtraction, division, we can define a new function. So I'll do addition as an example, and then you can extrapolate what it would look like for the other operations. So I'm going to define a new function, which is the addition of f and g. So this is called f plus g, is a function defined in the following way. So you should think of f plus g as like a symbol that is the name of that function. So this is the name of my function. And if I want to apply it to a specific x, then I would write it like that, just to distinguish from, if I didn't have these parentheses here, it might be confusing. Like it might just look like f plus g of x or something. So I just add parentheses here to make it clear that I'm adding the two functions f plus g. So this is defined to be f of x plus g of x. Right, so I know how to add two real numbers. The output of f of x is a real number. The output of g of x is a real number, so I can add those two things. So yeah, this right here is just a symbol, which is the name of the function. And you can also similarly define you could do f minus g, you can do f times g, and you can also do f divided by g, which we sort of already talked about when we talked about rational functions, for if the case when f and g are polynomials. Okay, then the other way to combine functions that we'll be using is the composition. So we'll have two functions, f and g. And these are going to be functions from R to R. Then the composition of f with g is the following thing. So it's written as f circle g, not to be confused with f times g. So you write like an open circle. And what this function does with an input x is it takes, so I'll just write this out first. So what it does with an input x is we're just going to compute what is g of x and then plug that back into f and then compute f of whatever that output was. Okay, so what do? You take x, plug it into g, and then plug that output into f. Okay, are there questions before I do an example of a composition of two functions? Okay, so let's do an example. So let's let f of x be the square root of x, and let's let g of x be x squared plus 2. Okay, so I'll compute f composed with g. Of x. Oh, let's just do a specific value. So let's do f composed with g of 5. Okay, so I have to compute f of g of 5. So what I'm going to do first is I'll just ignore the f completely and work inside of these parentheses. So then what I'm going to do is plug 5 into g. So I get 5 squared plus 2 by just plugging 5 into g. And then, so I'll simplify inside the parentheses, this is going to be 27. And then I compute f of 27, and I get the square root of 27. Okay, does that calculation make sense? Do I get the same thing if I switch the order of f and g? Yeah, no, you don't. So let's see what happens if you switch the order. So I'll just make room over here. So if I compute instead g composed with f of 5, so I would get g of f of 5. F of 5 is the square root of 5. So I would have g of square root 5. And then plugging root 5 into g, I would get square root of 5 squared plus 2. So then in the end, I just get 7. Okay, so you can see with this, the order of the composition really matters. And so I think, yeah, that's just a little caution. So when you encounter something like this, you have to remember like which one do you plug into first, right? So this is just like a feature of the notation that you have to remember. This means do G first and then do F to the output of that. Okay. Are there questions? Yeah.
I guess what's the reason for having this way of writing it as an alternative to just writing it as f of parentheses g of x, like to kind of let you do something or avoid some confusion that you like otherwise would be a risk of running into?
Yeah, so this, I guess this just allows us to refer to the function f of g of x, right? So now this, that operation of doing g and then doing f, like that thing has a name, and so we can work with that separately. Yeah. Was that? And there will be times when you're given a function and it will be helpful to think of it as a composition of functions. So for example, so this will be like sort of doing the opposite thing, but say you had the square root of x minus 5 cubed plus 7. Say I give this function to you. It might be helpful to break this down into two separate steps where it's like, okay, first we're taking square root of x minus 5, and then we're cubing it and adding 7. Yeah. Are there other questions? Okay, so let's talk about continuity. So this is going to be a big topic of conversation for the next few lectures. So what is continuity? This is a property of functions. And the basic intuition is that a function is continuous if I can draw the graph without picking up my pencil. So it's the kind of thing where a lot of times, if you are looking at a specific example, there's a very obvious like gut intuition about whether or not the function is continuous, because you can just look at it and say, no, I didn't have to pick up my pencil, or yes, obviously I had to pick up my pencil to draw this. But that intuition breaks down when you get into more complicated examples. So we're going to add another, so yeah, maybe I'll write down. So the intuition is that a function is continuous if you can draw the graph without picking up your pencil. And I want to give you another intuition that will be closer to the mathematically rigorous version. So this is like a second intuition, which is that no matter how much you zoom in, you don't see a break in the graph. So it may not be clear right now why we need a mathematically rigorous definition, right? Because it seems like the rule of can I draw the graph without picking up my pencil should be sufficient enough. So I'm gonna, before getting into the nitty gritty, I'm gonna look at some examples to see sort of like why do we need to go into more details about this thing that seems on the surface to potentially just be very simple. So let's look at the examples. Okay, so the first example that I want to look at is going to just be a function that is continuous everywhere. So this will just be a linear function. And I'll write this as L of x is equal to 2x. So here's what the graph looks like. So just be like a line through the origin with slope 2. Is this function continuous at every real number a? Yeah, clearly, like I just drew it without picking up my pencil, right? So this is a continuous function. So, okay, yeah, maybe I'll make this distinction now. So this is continuous at every real number. So then we say that the function is continuous everywhere. So when we write down the definition of continuity, it'll only be, how do you decide if a function is continuous at a specific point? And then if the function is continuous for every real number, then you'll say that the function is continuous. Okay, here's a second example. So this one will be called a removable discontinuity. And so my example for this one is going to be a piecewise function, r of x, which is 2x whenever x is not equal to 3, and otherwise it's going to be 9. So how does this thing look? How does the graph of it look? So let's just put x equals 3 right here. Then, okay, this is not to scale because I won't be able to draw the slope accurately with such a small picture, but so here's my function. At x equals 3, it's equal to something else, so we have a hole. And at x equals 3, it's equal to 9. This is like y equals 9. Okay, so is the purple? I'll make this pink instead. I feel like this purple is hard to see on the screen. Okay, so that is the graph of this function. So this one is not continuous at x equals 3 because I had to pick up my pencil to draw the picture. So this one is not continuous. But it is continuous elsewhere. And we call this a removable discontinuity because we could change the value of the function in just one spot and then the function would be continuous. So this is removable because I could redefine the function in one place to get a continuous function. Okay, are there questions about sort of these first two examples? Yeah. Yeah, I guess just making a new function that only differs from this function and one value. Yeah. So like I could write yeah. Yeah. I guess according to this definition that would be no longer removable. Yeah. But I think yeah, I mean like that is just it's still only problematic at a finite number of places. So I think that's still like a pretty yeah. Yeah. Other questions? Okay, so we're going deeper into the types of discontinuity. So these are going to get more and more like erratic. So the next example is a jump discontinuity. So for this example, I'll have j of x equal to 2x whenever x is less than 3 and 2x plus 2 whenever x is greater than or equal to 3. So here's how the graph would look. And here's x equals 3. So up to x equals 3, we just have this same linear function, and then we have a little hole here. And then at the value of x equals 3, we go up by 2, and then continue on with that same linear function. Okay, so this is also not continuous at x equals 3. And we can't just redefine the function at one place in order to make it continuous. So this is no longer just a removable discontinuity. It's like sort of a next level up. So can't redefine the function in just one place to get a continuous function. Okay, the next one, this is getting more and more wacky. So this one's called an erratic function. So for this one, I'm going to define e of x to be, let's say it's 1 whenever x is equal to 1/2, 1/4, 1/6, and so on. So whenever x is equal to 1 over an even number, the function is going to be 1, and otherwise it'll be -1. Okay, so how does this thing look? Okay, so let's say this is 1, this is 1/2, this is 1/4, and so on. We get smaller and smaller values, getting closer and closer to 0. So, and then this will be 1 and this will be -1. Okay, so how is my function looking? So it's gonna, for the most part, be a constant function at -1, but then it's gonna have a bunch of holes in it. So looks something like this. So we'll have a hole here, a hole here, a hole here, and then a bunch of holes getting closer and closer to the origin. And then up, and then on these values, it takes on the value 1. Okay, so clearly the function is discontinuous at these values, right? So whenever x is 1 over an even integer, the function is discontinuous. Discontinuous just means that it's not continuous. Is it continuous at 0? Let's have a vote. Who thinks? So raise your hand if you think that it is continuous at 0. Okay, raise your hand if you think it is not continuous at x equals 0. We have like maybe like 5 or 6 votes. And then who doesn't know or doesn't have abstains from a yes or no answer? Okay, so it seems like the sort of general feeling is probably no, but also it's confusing. So the answer is no. But sort of like based on our intuitive definition or our idea of what continuity is so far, I think it's not really clear. So like this sort of like flimsy idea of continuity that we have at this moment is insufficient to decide whether or not this function definitively is or is not continuous at zero. So I think like this is sort of an indication of where the waters can start to get murky. So I'll give you one more function where it's maybe even less clear whether or not it's continuous at zero. And this one is called the wiggly function. So I'm going to define w of x to be the following thing. So it'll be x times the sine of 1 over x. So this is a valid function whenever x is not equal to 0. So this is just going to be for x not equal to 0. And otherwise, this function is going to equal 0. Okay, so let's draw the graph of this. How does this thing look? Okay, so we know what sine of x looks like. It's just wiggling sort of back and forth. 1 over x gets really, really big as x approaches 0, right? So as I'm getting closer and closer to 0, I'm plugging in really big numbers into sine x. So I'm going to start wiggling faster and faster. So so maybe as an aside, I'll just say like sine of 1 over x, the graph is going to look something like this. Like it'll be wiggling slowly and then start to pick up more and more wiggles as you get to the origin, and then it'll spread out again. Does that make sense? So then what is x, the factor of x doing out front here? That's just going to scale this. So sine x goes back and forth from 1 to -1, right? If I stick an x in front of there, then the sine function is going to be wiggling back and forth between like these two lines, these two pink lines, right? So overall, this function looks like something that has big slow wiggles as you're really positive or really negative, but then as you get closer and closer to the origin, they get really small and fast. So I'll try and draw this. So maybe it's something like okay, don't come for me if this doesn't satisfy the vertical line test. It's meant to. I'm just not very good at drawing. So this is what this thing sort of looks like. So it does look like aside from x equals 0. Oh yeah, and of course we defined it specifically to be 0 when x is equal to 0. Okay, so it looks like aside from x equals 0, it is continuous. But as we approach 0, we get like infinitely many wiggles. So is the function continuous at 0? And I think like, so our original intuition was that the function was continuous if you could draw it without picking up your pencil. But since we have infinitely many wiggles, it's not even clear if we can draw the function at all, let alone without picking up the pencil. So like, can you draw something with infinitely many wiggles at all? And so I think this is where it starts to become really clear that we're going to need like a very structured definition of continuity in order to decide whether or not functions are continuous. So we need a better definition. Okay, are there questions? So here's the ingredients that we're going to need. We need 3 ingredients for a better definition. So the first thing that we're going to introduce is something called collapsing collections. And then we'll also need something called wrappers and images of intervals. So we're going to spend the next few lectures talking about these 3 ingredients, and sort of these will lay the groundwork for our definition of continuity. So maybe with the last few minutes, I'll just start giving you the idea of what a collapsing collection is, and then we'll pick up there next time. So collapsing collections. So the idea here is that in order to decide whether or not a function is continuous at a specific value, what we need to do is zoom in on that value and sort of see if when we zoom in, does it still sort of like look continuous. And collapsing collections is going to make precise what the like size of the zoom in windows is going to be. So to decide if f is continuous at a value a, we need to zoom in. So let's say we're looking at a equals 3 is our value of the function. So then here's like a possible collection of like zoom in windows. So I could start by just looking at, say, like the interval from 1, or let's go from 2 to 4. Okay, so 3 is directly in the middle of that interval. And then let's say I want to zoom in. So then my next interval could be 2.9 to 3.1. So now I've really like honed in on what the function is doing at that value 3, because I'm looking at I zoomed in pretty far, right? Like I'm only looking at something that is 0.2 wide. But you could go in even further, right? So remember back when we talked about the real numbers, we said we can just keep zooming in. There's always more real numbers in between any 2. So I could look at 2.99 to 3.01, and I could just keep zooming in as far as I want. So I could look at 2.999 to 3.001, and so on. So the key features of this like set of zoom in windows is that every interval is a subset of the previous one. Let's note every interval is a subset of the previous one. And also 3 is contained in every interval, right? That number that we're zooming in on is in every interval. And the last thing that I think is less clear, but maybe it'll make sense when I say it, is that 3 is, so if I continued writing down intervals following this pattern, 3 is the only number that's contained in every interval. Right, so if I pick a number that's not equal to 3, I can just zoom in so that I can no longer see that number. Yeah, do you have a question?
But is it right that the shrinking doesn't necessarily have to be symmetrical?
Yeah. Yeah, so we'll stop there for today. I'll write down the definition of a Claxon collection next time, but it'll be sort of like these properties, and you're right that it doesn't have to be symmetric. Yeah. Okay, I'll see you all next time.
That's a question.